Welcome to video lecture D3. This one is on determinants, column operations, and products. I'll be your caller, Tom Roby. Here are the outline and objectives. We'd like to analyze how column operations affect the determinant. We've already analyzed row operations, and we'll see that they're pretty much the same thing. And the reason for this connection is just that the determinant of the transpose of a matrix is the same as the determinant of the matrix. And then we'll prove that the determinant of a product of two matrices is the product of the determinants. This is a very useful property, and we'll apply it in some theoretical examples. And in practice, it's maybe not the most useful property, but it gets used quite a lot to understand things. So here's the first thing to understand. If you take a n by n matrix and you want to compute its, take its transpose and then take the determinant, that'll be the same as the determinant of A. All right, and so why should this be true? Well, really, it's just because the Laplace expansion works along any row or any column. So if you take a matrix and you take its transpose, then what have you done? Like, suppose you expand it along the first column. Well, first row, I mean, of A. Well, for a transpose, that would be expanding along the first column. You would have the same values, and all the other things would be transposed. So this isn't really a hard thing to understand. Of course, neither the book nor I have actually given you a careful proof that the Laplace expansion always works along any row or column. But taking that for granted, this property is easy to see. And so then we get a corollary, which is really the same thing that we did in a previous video lecture for row operations, namely that if you take a column of A and you rescale it by k, then that rescales the determinant by k. If you interchange two columns of A, that changes the sign of the determinant. And if you add a multiple of one column to another, then you don't change the determinant at all. All right. So here's a way to illustrate that. If you look at this matrix, I ask you to take the determinant. There are no zeros. It's not so obvious how you might expand it. And maybe it's not so obvious like how row operations would work nicely here. But if you notice that this first column and the third column have a nice relationship. Do you see what it is? Right, so the first column times 2, if I add that to the third column, I get a 0 column, right? So since I can do that, that means that the determinant of this matrix is the same as the determinant of this matrix where I've got a column of zeros in the third place. Right, and that's clearly 0 because I can just expand along that column. Okay, so there's a quick example where this might come in handy. All right, and so now the main part of this lecture is to understand why is the determinant of a product of two matrices equal to the product of the determinants. So this is a proof that'll take us a few minutes, but it's really not so bad. It's got 3 different parts. So the first part is, suppose that A was not invertible. The determinant of A was equal to 0. Then I claimed the determinant of AB must be 0. And if that's true, then this property would work. Because if the determinant of A is 0, then this product on the right-hand side is 0, so that had better be 0 if this property is going to work. And so why should that be true? Well, remember the determinant of, let's look at proving the other way. Suppose that the determinant of AB was not 0, then AB would be invertible, right, by the invertible matrix there. So if the determinant of AB were not equal to 0, that would imply that AB was invertible. And what does that mean? Just by definition, that means that there exists a matrix C such that AB times C is equal to the n by n identity matrix, right? That's what invertibility means, is that there's an inverse matrix. Okay, but now, I can't commute matrices, but I can rewrite this associatively. I can reassociate this as A times BC equals IN. Okay, but then BC is just an inverse for A, right? A right inverse, but we know that if you've got a one-sided inverse, then it has to be two-sided in this situation. Okay, so that implies that, so A is invertible, and that implies that the determinant of A is not equal to 0. So this is sometimes called proof by contrapositive. We wanted to prove that this implied this, And instead we proved that not this implied not that. If you take a higher level math class with proofs, you'll see this kind of thing happening all the time. But I hope that made some sense. Okay, so that's not a hard thing to see. And so now the next step in this argument, oh yeah, so now I'm just saying what I said. Because if A is not invertible, then AB is not invertible. So now the second claim is that if E is an elementary matrix, which elementary matrix means one that I get from the n by n identity matrix by just doing a simple row operation, then I claim that this property holds in that situation, that the determinant of EB is equal to the determinant of E times the determinant of B. So let's take a look at why that might be true. And here's the cool thing. Right, what are the three different kinds of elementary elementary matrices? Well, so there's the one where I add a multiple of one row to another. And so that might look something like this. And now I add, say, Q times row 1 to row 3. I'm not going to write down all the possibilities in a general way, but I'll just write down some examples that I hope will be convincing. All right, and so any matrix that looks like this, well, it's still going to be upper triangular. If I added a multiple of one row to another one, then it's either going to be lower triangular or upper triangular, depending on which way I did it, but it's still going to be triangular, and so the determinant of this is definitely going to be 1. Okay, so now let's think about another kind of elementary row operation. Well, what if I rescaled? Suppose I rescaled the middle row by k. So then that elementary matrix looks like this, right? So I've rescaled the identity matrix by putting a k in this row. Well, the determinant of that is just k now, right? And if I apply this matrix to another matrix, then I'm just rescaling the second row by k, and so that should multiply the determinant by k. Okay, so it's clear that the effect of this matrix should be nothing because its determinant is 1, so I'm just multiplying by 1. Here I'm multiplying by k, and now the last possible case is if I had something where I interchange two rows. So suppose I interchange rows 2 and 3, then I'd have 0, 0, 1, 0, 1, 0, say. Right? Okay, so there's my matrix, and when I interchange, the identity has determinant 1. When I interchange two things like that, then it changes the determinant by multiplying by -1. Right? But that's exactly what happens when I apply this matrix E to B, is that I've just interchanged rows 2s and 3. Okay? So it's easy to see if you just look at these elementary matrices that they exactly, when you apply them to a matrix and take the determinant, it's the same thing as if you took the determinant of the original matrix and multiplied by the determinant of this elementary matrix. Okay? And you're like, well, so what? I want to do this for more than elementary matrices. But here's the brilliance of mathematics, where we take something that's hard to see in general, and then we split it up into small pieces, each of which we can understand better. So now here's the proof for the general situation. Suppose that A is an invertible matrix. Then one of the parts of the invertible matrix theorem says that A has to be row equivalent to the identity. Okay? So that means that there's some sequence of row operations that I apply to the identity, I get A. I can go backwards and forwards with this. So let's just say I take E1, first I take E1 to A, then E2, and so on. So I have this product of L elementary matrices that I multiply in order times the identity, and I get A. All right? So now you can't stop me from finishing the proof, because what's going to happen? Well, I want the determinant of A times the determinant of the product of A and B. Okay? So A I can replace with this product EL through E1. And now by this property, just for the elementary matrix, I can split off the determinant of EL times the determinant of the rest. And then I can split off the determinant of EL minus 1 times the determinant of EL times the determinant of the rest. And I just keep doing this step by step, splitting off one elementary matrix at a time, just peeling them off until what I get is the determinant of EL times the determinant of EL minus 1, dot, 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 the determinant of E1, and then finally I'll have the determinant of B. Okay, but you tell me you wanted the determinant of A times the determinant of B. But see, once I've got the B split off, now each of these guys, I can just sort of put them back together one by one. And join them back up as the determinant of the product of E1 through EL, because this property works for elementary matrices. And that's just, this is just equal to A, so I end up with the determinant of A times the determinant of B. Okay? So it's really a nice use of very fundamental mathematical reasoning, and so I hope you were willing to bear with me and see how this all worked. And let's see. So now, let's think a little bit about some possible applications of this. I mean, it's really dull to, like, you know, take two matrices, take their determinants, and then multiply the matrices together and check that this is true. That wouldn't be so interesting. So let's do something that's got a little bit more mathematical meat to it, and say, suppose that the determinant of A to the fifth is equal to 0. Could A be an invertible matrix? And I say to you that no, indeed, it could not, because what do I know about, if I know that the determinant of A to the fifth equals 0, then 0 is equal to the determinant of A to the fifth, which is equal to the determinant of A to the fifth power, because I can just use this property 4 or 5 times to get that it's the product of this determinant. But so now I've got some number, determinant of A is just a number. I raise it to the fifth power, I get 0. The only way that can happen is if the determinant of A is equal to 0. So note that it's not true that if A to the fifth is 0, that doesn't imply that A is equal to 0. But if the determinant of A to the fifth is 0, then the determinant of A has to be 0. Okay? So that's the answer to question 1. Question 2. How would you compare the determinant of AB with the determinant of BA? So think about it for a second. Right? Remember that AB and BA are in general quite different matrices. There's no reason that they have to look anything alike. So why should the determinants have anything to do with each other? Well, the answer is this property, right? Basically, this property says that they're both equal to the product of these two numbers, right? So the determinant of AB is equal to the determinant of A times the determinant of B, but that's the determinant of B times the determinant of A, which is the determinant of BA. Okay? So once we get down to the level of numbers, numbers do commute even though matrices don't. So it's a useful thing to keep in mind when you're trying to look at properties of matrices. And now here's one other thing that's worth thinking about. So a matrix U, a square matrix U that satisfies the property that you multiply it by its transpose, you get the identity. If that's true, then also U transpose times U is equal to the identity. They have to be two-sided inverses. Then what can we say about the determinant of U? Okay? These matrices that satisfy this property, by the way, are called orthogonal matrices. They'll come up quite a bit in the later part of this course. They're very useful. So what can you say about the determinant of such a matrix? And so the answer is that it's not very flexible, right? Because I know that if I equals UU transpose, then certainly the determinant of I is equal to the determinant of UU transpose, which is the determinant of U times the determinant of U transpose. Okay? Well, what's the determinant of the identity matrix? That's just 1. So that means that 1 has to be equal to, I've got determinant of U times the determinant of U transpose, but we just saw earlier, right, that this is equal to the determinant of U. So this is just equal to the determinant of U times itself, so the determinant of U squared. So now I've got this thing is some real number. When I square it, I get 1. What could it be? Well, the only possibilities are that the determinant of U is plus or minus 1. Okay? So the determinant of an orthogonal matrix has to be plus or minus 1, and that actually is saying something geometrically, that the orthogonal matrices don't stretch or shrink things when you think of them as linear transformations from Rn to Rn. We'll talk a little bit more about that in upcoming video lectures. But that's all for video lecture D3. Thank you as always for your kind attention.